NASA's Adventurer 1 transport, the furthest journeying transport ever sent, continues its shocking trip through the universe for almost 50 years. Wayfarer 1 has been sending back vital information from the farthest reaches of the universe, greatly advancing our understanding of the cosmos. However, recent transmissions from this astounding spacecraft have presented puzzling signals that have left the entire space community in a state of wonder and bewilderment. These signals have sparked debates about whether they are the result of a technical glitch or if they could be indicative of something far more extraordinary, such as extraterrestrial activity. Join us as we dive deeper into the mystery surrounding these remarkable transmissions and uncover what might be lurking in the depths of space. Mankind's curiosity about the mysteries beyond our planet has been a fundamental driving force in space exploration since its inception. This insatiable curiosity prompted the historic launch of missions like Explorer 1 and Voyager 2, which were among the most ambitious space ventures of their time. The launch of Voyager 2 from NASA's Kennedy Space Center on August 21, 1977, marked the beginning of a new era in space exploration. Just 14 days later, on September 5th, Voyager 1 followed, paving the way for an extraordinary journey. These twin transports, each weighing around 720 kilograms, roughly equivalent to a small car, were launched during a unique alignment of the outer planets, which played a critical role in their trajectories and mission outcomes. Throughout their remarkable odyssey, these spacecraft traveled in disparate directions and at different speeds. A pivotal moment occurred on December 15, 1977, when Voyager 1 surpassed its twin due to differences in their paths. Since then, Voyager 1 has emerged as an essential asset, providing vast amounts of data that have revolutionized our understanding of the universe and its numerous phenomena. Before we dive into Voyager 1's latest astonishing discovery, which has captured the attention of the entire space community, we should revisit some of its most notable achievements. In 1978, during its Jovian imaging mission, Voyager 1 was positioned about 265 million kilometers from Earth. By January 1979, it had embarked on a magnificent 100-hour mission, capturing an enchanting time-lapse film of Jupiter's rotation. This series of 3,750 images offered incredible perspectives of Jupiter's dynamic atmosphere and its intricate features. The spacecraft's discoveries included the detection of a faint ring around Jupiter and 2 previously unknown moons, significantly expanding our knowledge of the gas giant's complex system. To ensure the spacecraft's safe passage and avoid potential contact with Titan, one of Saturn's moons, corrective maneuvers were executed. After the successful Saturn mission, scientists decided to conclude the planetary mission of both Voyager 1 and Voyager 2. However, the spacecraft were sent on a new trajectory, venturing beyond the boundaries of our solar system at an astonishing speed of 325 million kilometers per year. In January 1990, the interstellar mission began, with Voyager 1 continuing its sublime voyage. During this period, Voyager 1 made significant discoveries, including the identification of 4 additional moons, Mimas, Enceladus, Tethys, and Rhea, and captured some of the most extraordinary images taken of our solar system. On February 14, 1990, Voyager 1, positioned about 6 billion kilometers from the Sun, embarked on a visual journey known as the Family Portrait, capturing breathtaking images of the solar system's planets. This collection of 60 images added to Voyager 1's impressive total of 670 photos taken during its encounter with Neptune. Voyager 2 also achieved remarkable milestones during its mission. As it approached Neptune, it recorded wind speeds exceeding 13,100 meters per second, the fastest winds ever observed in our solar system. This achievement provided valuable insights into Neptune's distant atmosphere and its largest moon, Triton, whose surface temperature plummets to a frigid -391 degrees Fahrenheit, making it one of the coldest places in our solar system. Triton also exhibited remarkable features, including ice volcanoes that erupted nitrogen gas and propelled frozen particles 5 kilometers into its hazy atmosphere. These extraordinary discoveries have expanded our understanding of the diverse and complex nature of celestial objects in the outer regions of our solar system. The Voyager missions have delivered significant and groundbreaking results. Voyager 1 and Voyager 2 revealed that Jupiter and Saturn's moons, once believed to be heavily scarred and dormant, are actually interacting with geological activity. Voyager 2, in particular, achieved several notable accomplishments, including being the first spacecraft to fly by Uranus and Neptune, and it remains the only spacecraft to have done so. NASA employed various methods to extend the operational lifespan of these ambitious spacecraft, including shutting down non-essential instruments and systems to conserve energy. The mission is expected to conclude in 2030, marking a moment of pride and a tinge of sorrow for the scientists and engineers who have dedicated themselves to this remarkable undertaking. The design of Voyager 1 and Voyager 2 was a marvel of engineering, allowing them to endure the harsh conditions of deep space for decades. Designing these shuttles was planned as steady stages, turning at a rate in excess of multiple times slower than a clock's hour hand. This design decision reduced visual obscuring as the shuttle crossed the vast breadth of space. Even before reaching the outer planets, the shuttle began sending pictures of Jupiter, revealing its swirling clouds and notable features. The Great Red Spot, a massive storm on Jupiter, dazzled audiences at NASA's Jet Propulsion Laboratory. However, the discovery of active volcanoes on Jupiter's moon Io garnered the most attention. The shuttle's instruments detected astounding signs from Io, which were confirmed by stunning images showing towering volcanic plumes and a surface scarred by eruptions. One of Io's most prominent volcanoes erupted with a force several times greater than that of Mount St. Helens, covering an area almost the size of France. As the spacecraft continued their journey, their cameras were eventually turned off to conserve power and memory before they ventured into interstellar space. Remarkably, the images they captured did not include Mercury or Mars due to various factors. Besides the Voyager missions, NASA has launched other exceptional spacecraft, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Pioneer 10 surpassed Pioneer 11, becoming the spacecraft farthest from Earth. Despite the absence of other space probes to observe it, Voyager 1 continued its lone journey for an additional 14 years before entering the interstellar medium on August 25, 2012. The advancement of the Voyager missions was made possible through various innovative techniques, with gravity assist maneuvers standing out as particularly brilliant. These maneuvers were essential for moving the spacecraft to their distant destinations and gathering critical data. The spacecraft relied not only on their own propulsion systems, but also on gravity assists to achieve their goals. Imagine the two bold rockets gracefully navigating through our solar system, using the gravitational pull of planets to propel themselves forward. This celestial dance allowed them to conserve fuel and achieve the necessary speeds to explore various locations. Gravity assist maneuvers involve giving the spacecraft a small amount of a planet's energy as it passes by with extreme precision. For example, as Voyager 1 approached Jupiter, the planet's massive gravitational pull accelerated the spacecraft, increasing its speed. Achieving such precision was crucial. Any deviation from the correct angle or speed could have resulted in disaster. Despite the staggering accuracy required, the brilliant minds behind these missions successfully executed these gravity assists many times, sending the spacecraft on an extraordinary journey. The grand voyage, made possible by these celestial maneuvers, saw Voyager 2 utilizing gravity assists from Jupiter and Saturn to reach Uranus and Neptune. The success of the Voyager missions owes much to these gravity assists. As we reflect on the incredible journey of these exploratory spacecraft and the wealth of information they have provided, we eagerly await further updates on the investigation into Voyager 1's recent anomalies. Both Voyager 1 and Voyager 2 continue their missions beyond conventional limits, and their accomplishments include exploring Jupiter and its moons, Saturn and its moons, Uranus and Neptune. Voyager 1's time-lapse images highlight 10 rotations of Jupiter in striking detail, including the discovery of new moons and a small ring. These discoveries have greatly enhanced our understanding of Jupiter's complex system. Voyager 1 also discovered 4 additional moons of Saturn, Mimas, Enceladus, Tethys, and Rhea, and took remarkable photographs of Saturn and its rings, providing new insights into Saturn's intricate system. The spacecraft made history by visiting Uranus and Neptune, delivering valuable data about their atmospheres and moons, advancing our understanding of the outer regions of our solar system. After completing their planetary missions, Voyager 1 and Voyager 2 ventured into interstellar space, gathering data on the interstellar medium. This ongoing investigation continues to expand our knowledge of the universe beyond our solar system. As we await more information about Voyager 1's latest signals and their potential implications for our understanding of the universe, the remarkable journey of the spacecraft remains a source of inspiration and fascination for scientists and space enthusiasts alike. Their iconic achievements continue to push the boundaries of human knowledge and exploration, highlighting the incredible potential of space discovery. Missions have furnished us with a goldmine of data about our nearby planet group and beyond. The notorious pictures and data of the spacecraft have also delivered a brilliant record, a captivating artifact designed to share the story of our world with extraterrestrials. This record contains sounds and images chosen to represent the diversity of life and culture on Earth. It includes greetings in 55 languages, music from various cultures, and a selection of natural sounds such as thunder and whale songs. This message in a bottle, so to speak, reflects the hope that one day, if intelligent life exists elsewhere, they could find and understand it, offering a glimpse into mankind's essence. Explorer 1 and Explorer 2 were equipped with scientific instruments that have revolutionized our understanding of the universe. These instruments included magnetometers, plasma wave detectors, cosmic ray instruments, and imaging systems, each contributing crucial data about space phenomena. For example, the magnetometers have provided insights into the magnetic fields of Jupiter, Saturn, Uranus, and Neptune, revealing the complex interactions between these planets and their surroundings. The plasma wave detectors have helped us grasp the nature of the solar wind and its relationship with planetary atmospheres and magnetospheres. One of the most remarkable aspects of the Explorer missions is their ability to measure the heliosphere boundary, a massive bubble of solar particles and magnetic fields that encloses our solar system. As Explorer 1 approached the edge of this boundary, it detected the sudden change from the solar wind to the interstellar medium. This data has been instrumental in shaping our understanding of the heliosphere's structure and its role in protecting Earth from cosmic radiation. The spacecraft's observations have provided evidence of a distinct boundary where the solar wind slows down and becomes denser, known as the termination shock. Beyond this point lies the heliosheath, a region where the solar wind interacts with the interstellar medium, creating a complex and dynamic environment. Explorer 2's journey has been equally significant. After its successful flybys of Jupiter, Saturn, Uranus, and Neptune, it has continued to provide valuable data on the outer reaches of our solar system. Explorer 2's observations of Uranus were particularly surprising, revealing its unique magnetic field, which is tilted significantly compared to the planet's rotation axis. This discovery challenged existing models of planetary magnetism and spurred further investigation into the magnetic conditions of other celestial bodies. In addition to their scientific contributions, the Explorer missions have profoundly impacted public interest in space exploration. The stunning images of distant planets and their moons, combined with the personal stories of the spacecraft's journeys, have captivated the imagination of people worldwide. The images of Saturn's rings and the detailed views of Jupiter's moons, particularly Io's volcanic activity, have inspired countless individuals and have been featured in educational materials, documentaries, and popular media. These missions have fostered a sense of wonder and curiosity about the universe, highlighting the importance of exploration and the quest for knowledge. The engineering and logistical achievements accomplished by the Explorer missions are also significant. The spacecraft were designed to operate in extreme conditions far from Earth, with temperatures plunging below -220 degrees Celsius. They rely on radioisotope thermoelectric generators, RTGs, for power, which provide a reliable energy source despite the vast distance from the Sun. The engineers who designed and built these spacecraft faced numerous challenges, including ensuring that the instruments would remain functional for decades and that communication could be maintained over such vast distances. The data returned by the Explorer missions has also influenced our understanding of the broader cosmic environment. The spacecraft have helped map the distribution of cosmic rays and have provided insights into the density and composition of interstellar dust. This information is crucial for understanding the conditions in the space between stars and for planning future missions that could explore other star systems. As the explorers continue their journey into interstellar space, their legacy is cemented not only by the data they have already provided, but also by the inspiration they offer for future exploration. The missions have paved the way for new technologies and ideas in space science and have set a precedent for ambitious, long-term space missions. They demonstrate the possibilities of human ingenuity and the value of perseverance in the face of daunting challenges. Looking ahead, the Explorer missions have inspired a new generation of spacecraft and missions. Concepts for future probes aim to build upon the Explorer's achievements with the goal of exploring even more distant regions of space. These upcoming missions will continue to push the boundaries of our knowledge and will benefit from the foundations laid by the Explorer spacecraft. In conclusion, the Explorer missions represent one of humankind's most significant achievements in space exploration. Their contributions to science, their role in advancing our understanding of the solar system and beyond, and their impact on the public imagination underscore the importance of continued exploration and curiosity. As Explorer 1 and Explorer 2 travel further into the universe, they remain symbols of human ambition and the unending quest for knowledge.